Good morning, everyone, and welcome to the fifth SPARC webinar. This time we have homegrown professors from Northeastern, Matteo Rinaldi and a research professor, and both of them are also founders of a startup called Zappster. And for specific details on their very impressive bios, please check the link on the SPARC webinar invitation. And with that, I'd like to hand it over to Matteo and Zhenyun.
All right. Good morning, everyone. Thank you very much, Emel, for the introduction, and also thanks to Tiffany and Michael for organizing this and really giving us the opportunity to present our work in this webinar. So we are really excited to share our progress on the near zero power integrated microsystems for the IoT. So when we talk about the Internet of Things, we really talk about the deployment and maintenance of a very large number of battery-powered wireless sensor nodes. And often these sensors are deployed in environments that are challenging, environments where power might not be always available, and where energy harvesting might also be not always available. So in these case scenarios, energy is really the key challenge. And so here I'm just giving you a couple of possible, deployment scenarios as examples. So here you see, wireless sensor nodes that are deployed over acres of a crop field to monitor in real time different kind of plant health parameters for precision agriculture, digital agriculture kind of applications. And another application case scenarios is related to DoD kind of stuff. And here you can see where there are wireless sensor nodes that are deployed over a battlefield, for example, to monitor in real time potential intrusions in a perimeter. So in these, when we deal with so many sensors deployed in such challenging environments, frequent battery replacement is not only impractical, but it can even be dangerous and certainly is not sustainable from a cost perspective. So now an interesting thing to note is that for the great majority of IoT applications, like in these two examples that I'm showing here, sensors are often deployed to detect events that are time critical, or in other words, you don't want to miss them, but they are relatively rare, right? So in these case scenarios, now if you look at the power use in these wireless sensor nodes, well, you quickly realize that the great majority of the battery energy is wasted for continuous monitoring of the environment and processing of what the sensor is actually seeing. And only a tiny fraction of the energy, of the battery energy, is instead consumed to perform useful functionalities, like, for example, to communicate the detection of an event of interest when that event of interest is actually happening, right? So now the idea is that if we can completely remove these waste of energy when the sensor is standby monitoring the environment, we can dramatically extend the battery lifetime of the sensor. So in this kind of IoT kind of applications, well, if you can completely eliminate the standby power of the sensor, you can extend the battery lifetime from the typical, days, weeks, or months, then up to, perhaps 10 years or so, where, the lifetime of the sensor will be substantially limited only by the self-discharge of the battery itself. So that's really the basic idea behind what we are trying to do. But let me go into a little bit more details about this. So here I'm showing you a simplified schematic representation of a typical, wireless sensor nodes for some sort of environmental sensing. So the unit is typically composed of three elements. There is the front-end sensor, there is a back-end response device, and there is a battery unit. So the front-end sensor is really the sensing element that is capable of detecting the variation in a very specific environmental variables of interest, right? And so when it detects that change in the environmental variable of interest, the front-end sensor substantially activates the back-end response device that, depending on the particular application, or deployment scenarios, it can be different things. It could be, triggering a camera, a transmitter, an alarm, and so forth, right? So now the problem with state-of-the-art wireless sensor technology is that this front-end sensing element continuously drains power from the battery. Right? So even when nothing relevant is happening, the sensor is still draining power from the battery. And because of that, since, as we said before, the sensor spends the majority of the time while in standby, the majority of the battery energy is really wasted while monitoring the environment when nothing relevant is actually happening. And only a tiny fraction of the battery energy is instead used to perform the actual useful functionality, which basically is triggering the back-end response device to communicate somehow the event of interest. So now the idea here is that if we can now replace that front-end sensor with a completely passive, event-driven, zero-power microsystem, right? Then we can dramatically reduce the waste of energy in standby and consume battery energy only when something relevant is happening. So here the idea is to build a completely passive microsystem that can continuously monitor the environment without consuming any power, without draining any power from the battery. But the sensor, this passive sensor, is capable of detecting and discriminating very specific signature that is associated with a possible target of interest. Okay? So when the sensor detects and discriminates that signature, it's capable of taking the energy contained in that signature itself to basically connect the battery to the back-end response device to trigger the communication functionalities. So this approach, of course, as I mentioned before, completely eliminates the standby power consumption of the sensor, and it extends the battery lifetimes from months up to 10 years or so. So now, what is this physical signature? So the physical signature substantially is a combination of different kinds of signals, right? It could be physical signals, could be chemical signals that are somehow characteristics of an event of interest that we want to detect. So it could be a combination of vibration, it could be a radio frequency signal, it could be an acoustic signal, but it could also be light, and particularly interesting for some of the things I'm going to talk about today is light in the infrared portion of the spectrum, right? So that's what I'm going to focus in the rest of this talk. So basically a passive microsystem that can continuously monitor the environment without consuming any power, but is capable of detecting and discriminating the very unique infrared spectral signature of a possible target of interest. And when the sensor detects and discriminates that infrared signature, is capable of taking the energy contained in the infrared radiation itself to actually connect the battery to the back-end response device. It could be a radio camera or so forth. So really, this is the basic idea that what we want to do. And the basic device, I'm going to talk quite a bit about that during this presentation, but the basic idea is really to build a tiny mechanical switch that is triggered by infrared light at a very specific wavelength. And so here you see an actual picture of the device that I'm going to describe during this talk. But what is kind of interesting is that I'll show you how we can design these tiny micro-mechanical switches to detect very specific wavelengths of infrared radiations. And on the same chip, right, we can build arrays of these switches, and each of these switches can be designed to detect a very specific wavelength of infrared radiation. So in a very tiny compact form factor, we can substantially build a sort of passive spectrometer, right, that is capable of connecting the battery to the back-end response device only when a very specific spectrum, or let's say signature, a combination of infrared wavelengths, is actually coming from a target of interest. So now let me talk a little bit about the device. So this it's a highly simplified schematic representation of the device, just to illustrate the working principle, and then I'll go a little bit more into the details and the specifics of the designs that we are using. So, the device is substantially composed of a micromechanical bimorph cantilever. So substantially, this is a cantilever that is formed by a stack of two materials with two different coefficients of thermal expansions. So in other words, it's a cantilever structure, it's a microcantilever structures that when the temperature of this cantilever changes because of this difference in the thermal coefficients of expansions of the two materials forming the cantilever, the cantilever bends down when the temperature increases. So now, as you can see from this schematic representation, this bimorph cantilever at one end has a contact tip, while at the other end is connected to the substrate to a thermal insulator, so a thermally insulating region. So now also somehow here in this schematic representation, you can see that integrated on the top surface of this cantilever, there is a metamaterial infrared absorber. So this is it's a deeply sub-wavelength structures that can very effectively absorb infrared radiation at a very specific wavelength that can be lithographically defined by the geometry of these structures that we define on the top surface of the microcantilever. So, so this is the basic structure, and the working principle at this point is relatively simple, right? So when the device is exposed to infrared radiation that matches what this metamaterial absorber can absorb, right? The radiation is effectively absorbed by the metamaterial that is thermally connected to the cantilever. So now the heat here cannot flow really anywhere, right? Because it's very well thermally isolated from the heat sink from the substrate. So basically the cantilever heats up, and because it's up, as I explained before, it curves down, basically changing the vertical position of this contact tip that eventually gets in contact with another electrode on the opposite side, right? So basically, we can control this gap that separates these two electrodes by the impinging infrared radiation. So that's really the basic working principle. Now let me go into a little bit more details of actually how we implement these devices. So here you see, a more realistic representation of the devices. The device is composed of two cantilevers facing each other. So each cantilever is composed by a head, an inner pair of thermally sensitive bimaterial legs, an outer pair of thermally sensitive bimaterial legs that are used for compensation. I'm going to explain what that means. And these two pairs of thermally sensitive legs are separated by this thermal isolation link. So it's pretty much a narrower, cantilevers, or I would say narrower beam structure that acts as a thermal isolation region. So now on the head of the cantilever that carries the contact tip, we pattern this plasmonic metamaterial absorber. Again, I'm going to talk a little bit more about that later, but substantially it's a metal insulator metal structure, right, in which the top metal surface is patterned using these plasmonic nanostructures, these sort of patches that you see here that are in the range of hundreds of nanometers up to a micron on side dimensions of these structures. And basically by changing the lateral dimensions of these fissures on the top metal of this structure, we can basically select the wavelength of infrared radiation that gets very efficiently absorbed in this deeply sub-wavelength dielectric. So here we're talking about only a few hundreds nanometers dielectric, and we can achieve absorption in the mid-infrared range or so. So that's what is on the cantilever head that carries the contact tip. While on the opposite, on the head of the opposite cantilever, substantially we have a fully reflective surface that basically reflects the infrared radiation. So now you can see here a zoom in of the contact tips, and there is a tiny air gap. So this is in the order of a few hundreds nanometers, depending on the particular designs, that separates the contact tip from the other electrode that is on the opposite side of the cantilever. Okay, so now let's see how this works. So when the device is exposed by infrared radiation matching the plasmonic absorber that is defined on the plasmonic head of the cantilever that carries the contact tip, well, the radiation is efficiently absorbed And that causes a large variation in temperature of the structure up to this thermal isolation region. So here, what I'm showing here is a finite element method simulation that really shows the temperature distribution when infrared radiation is absorbed in this plasmonic head of the cantilever. So basically, you see that the inner pair of thermally sensitive legs, the temperature of the inner pair of thermally sensitive legs increases, right? And that translates directly in a bending downwards of those cantilevers, and therefore a vertical displacement of the head, and therefore the contact tip, right? That separates that is on the plasmonic head. So in other words, the air gap that separates the two contacts is really controlled by the impinging infrared radiation through a plasmonically enhanced thermomechanical coupling, right? So despite the fact that this structure is so sensitive to infrared induced temperature increase of the structure, right? The structure is instead completely immune to ambient temperature variation and residual stress that we might have in the thin film materials that are used to build these microcantilever structures. And that is really due to the use of these outer pair of thermally sensitive legs, right? That substantially, perform a sort of an in situ compensation mechanism for ambient temperature variation. So what you can see here is that if we have an ambient temperature variation, for example, both the inner and the outer pair of thermally sensitive legs will bend in the same direction, and that will translate in substantially no displacement of the head of the cantilevers. So, and then here you see, the actual, deflection of the leg and the head, right, with ambient temperature change, and you can see that basically the gap that separates the two contacts does not change at all if there is any kind of common mode variation in this structure. It could be ambient temperature variation, or it could be residual stress, in the thin film materials that are used to build these structures. So that's quite important, right, in order to achieve low false alarms rates in these kind of devices. Okay, I'm not going to go into all the details of the microfabrication process that we use to build these structures, but I just want to point out that it's a pretty, I would say, standard MEMS process. We do not use any kind of exotic material. It's really based on silicon oxide, aluminum, and we do use gold for the plasmonic absorbers, but other materials could also be used for integration with, for example, CMOS or electronics. So the only thing that I want to highlight, it's one of the I think design features that they were I believe very successful, and really they were key, right, for the demonstration of the functionality of the device, is really has to do with the design of the contact tip. Right? In principle, you could use this sort of simple planar design for the metal contact tip. But instead, we came up with this bowl-shaped design, that you can see here, that allowed us to use a very thin film material, metal electrode, right, that simplifies this microfabrication process. But at the same time, using this thin film material allows us to build contact tip that they are stiff enough, right, to provide stable and repeatable mechanical contact with the bottom electrode. Right, so basically, by using this bowl design shape, we can get sort of a 3x better stress handling and stiffness compared to what we would get with a planar tip design using the same thickness of the metal layer. And we can achieve this interesting tip design with more than 95% yield. So that's really something that I wanted to highlight, because also you will see that later on in some of the devices that I'm going to show you. So here it's an SEM image of one of the fabricated devices. And so I want to highlight some of the important features that I've discussed so far, and you can actually see them now in this implemented device. So first of all, you can see that, because of residual stress in the thin film materials to use to fabricate this structure, when we release these cantilevers, right, from the substrate, these are the devices are anchored here at these points, right? But otherwise they are suspended, right? They're free to move. So because of the residual stress, there is a certain amount of bending moment, right, induced in these, cantilever structures. But as you can see, that the amount of bending moment is the same that we have in the inner and the outer pairs of cantilever structures. And because of that, the legs, they bend in the same direction, right? As you can see here, both cantilevers, the legs, they bend in the same direction. And because of that, there is really no displacement here at where the contact tip is. And you can see here a zoom in of the actual contact tip. So here you see the bowl-shaped tip that I described before. And here there is a tiny air gap. So in this particular device is in the order of 500 nanometers that separates the two contacts. So this is really critical feature, because as you can imagine, controlling this gap, with the fabrication process it's quite important to have, sort of a stable detection threshold for these kind of switches. And you can see that this in situ mechanism that we integrated in the design of the structure, it's really effective and in achieving that. Also, I want to point out here the B material structure that I described before. So it's about 2 micron of silicon oxide, and on top of that, there is 500 nanometer of aluminum. So those are the 2 materials with the 2 different thermal coefficient of expansions that create the bending upon exposure to a temperature variation. And also the last thing I want to point out here in the plasmonic head that carries the contact tip, you can see that we have this very nice plasmonic structure. So these are metal patches. The dimension of these metal patches in the order of a micron or so. But I want to point out that we really, put some effort in achieving smooth edges here for these structures in order to get very sharp absorption peaks. And that's what I'm showing here. It's possible to build these plasmonic structures to achieve extremely sharp absorption features. So you can build lithographically, right? On the same chip, you can build devices that can absorb very specific wavelengths of infrared radiation with very, very high spectral selectivity, and at the same time very high absorption efficiency. So close to unity absorption with a full width of maximum that is less than a few percent or so. So that's really an exciting feature. And as I mentioned before, now you can connect a large number of these devices, forming some sort of passive logic circuit that connects the battery to the load only when a very specific combination of wavelengths is present. Right? And so that's what you can see in this sort of experiment. So you can see a device turn on only when it's exposed to the wavelength that it was designed for, but otherwise it will stay in the off state. So, this really allows us to build this sort of miniaturized spectrometer. So here you see an example of a 4-bit infrared digitizers that we were able to build using these devices. So we can build also a lot of different tricks integrated in these structures in order to reject wavelengths that we don't want to trigger the device, right? And here you see a clear example of that. So I mentioned before we can pattern a reflector on the opposite head of the plasmonic cantilever, but we can also build a sort of a complementary metamaterial absorber, right? That you basically bend down this opposite cantilever when the device is exposed to a wavelength that we want to reject. So this is a clear example where, for example, we want to detect CO2, but we want to reject NO2. So we can build these in the structure. And here is an experimental demonstration of that really shows that by these design tricks, we can really achieve absorption and detection when it's exposed to a specific wavelength, but we can reject different wavelengths, or we can reject broadband infrared radiation, for example. So that's kind of critical to achieve high, low false alarm rates. So I show you that we can detect very narrow spectral features, but we can also design absorbers that can, absorb in a broader band, like, for example, can be designed to absorb the radiation that comes from a human body, so in the 8 to 14 micron range. So, it's a slightly different design of the plasmonic absorber. So it's a much simpler, absorber design, but we succeeded. We built this kind of devices as well. And, just to give you an idea right now, so how we can use these devices to detect, for example, potential target of interest, right? In the case of a human body, we went ahead and we calculated, we measured with a calibrated, sensor, the amount of power that we would be able to receive from a human body at a certain distance. And here you can see different values of power depending on, if you're looking at the front of the body, if you're looking just at the head, or for example, just a hand of a human body. So based on that, we really, went ahead and we optimized the design of the device to achieve this very low actuation threshold, right? So it has really to do with the design of the structure, the control of this nanoscale gap that allows us to achieve it on state, right? So the switch will turn on when it's exposed to the amount of power that is radiated from a human body at a distance of 10 feet or so. So that's what this design optimization we did, and then let me share with you some results. So here you can see, for example, some experimental results that we achieved exposing the device that here is in this testing chamber. When we expose the device to a hand of a human body, so that's enough actually to trigger on the response of the device. And so that's kind of interesting. And let me show you also this quick video. So here you see basically again the device is in that testing chamber, and at a distance of several meters, here you can see that when I come in the field of view of the sensor, suddenly here you can see, let me show you one more time. So this is the multimeter that shows the current through the electrodes of the device, right? So it's off in this state. There is no current, but as soon as I get into the field of view of the sensor turns on. So this is really interesting, right? Because before the target of interest is when the target is not in the field of view of the sensor is not draining absolutely no power from the battery. But as soon as it gets into the field of view of the sensor, well, the sensor turns on and it can activate any kind of response device. So very quickly, let me just show you also the fact that we built some sort of system level demonstration of these devices. So not only in a lab, but we also package these devices in pretty conventional infrared ceramic vacuum packages. And we also sort of demonstrated an equivalent of a pyroelectric motion sensor detector with our technology. So this is a schematic representation of the lowest power available on the market pyroelectric motion sensor detector. So you can see here you have the pyroelectric sensors, conditioning electronics, microcontroller, and a battery unit. So basically what we were able to do is to replace the pyroelectric sensor and all the active electronics with our zero power sensor that now is used to simply control the connection between the coin battery and the wireless microcontroller. So basically, by doing that, we could drastically reduce the standby power consumption of this unit to pretty much equal to zero. And we can use this device also in sort of RFID tag kind of application for batteryless operation as well. So this really shows the incredible advantage of this technology that not only includes passive signal processing, right, in this kind of wireless sensors, but it does that without consuming absolutely any power in standby. So, and these are the kind of applications we are looking at now with our startup, Zappster technology. So we are looking at applications in the space of occupancy sensing or people counting, of human detection, as well as flame detection. As you can imagine, right, we can detect very specific wavelength of radiation. So that's significant for flame detection. We are also looking at applications in the area of smart farming. So it turns out that infrared radiation can provide information on the water content level in plants, right? So that's a significant, application for that technology, as well as, realizing zero power optical receivers for optical communication. And with that, I'm gonna give and pass the virtual podium to Zhenyun, that is gonna talk a little bit about what we have been doing with our startup company, Zappster. Zhenyun.
Thank you, Matteo. So here we would like to highlight the market opportunity in fire monitoring application. Fire accident can damage multiple buildings or installation within a very short time. The value of the assets destroyed during a fire can be tremendous. Persistent and ubiquitous fire monitoring could help us preventing these disasters. Nowadays, the fire sensor market is dominated by smoke, heat, and flame detector technologies. While smoke and heat detectors are cheaper compared to flame detectors, they are also generally much slower and less accurate, which makes them not suitable to operate in several environments. Moreover, none of the existing fire detection technologies can deliver a highly distributed monitoring system. Existing fire sensors are too expensive and cost too much power to be deployed with high granularity in most environments that face a high risk of fire. The main technological challenge is that the commercially available fire sensors use power continuously to monitor the environment and process what they see while there's no fire to be detected. Because of this waste of energy, when the sensor is in standby, the battery lifetime is limited to only a few weeks. When we deal with so many sensors deployed in large and complex environments, such as commercial buildings or a construction site or a forest, for example, frequent battery replacements is not only impractical, but it can be even dangerous and certainly not sustainable from a cost perspective. So our value proposition, therefore, is really to help infrastructure operators and landowners to protect people and assets from fire by detecting flames instantly with affordable wireless sensor that lasts 10 years. The Zappster as a zero power infrared detector technology really enables the extraordinary flame detection capabilities with long lifetime, wireless connectivity, and very small footprint. We really think the off-put alert feature of our technology.
I think, Zhenyun, you need to come to conclusion quickly.
Sure, yeah. We really think the off and alert technology feature of technology could be disruptive in fire monitoring of complex commercial structures. In particular, we think the beachhead could be fire monitoring construction site, where we were working on the customer discovery in this particular user segment. The main reason for that, for these disasters of existing fire monitoring system are suitable to operate in such a complex environment. Conventional smoke detectors do not work in dusty or open environment. In fact, the regulation forced to disable them if they're installed in construction site to avoid continuous false alarm. Flame detection in this case is preferred for early detection because of the presence of flammable materials and long detection range. However, all the existing flame detectors too expensive and power insufficient, efficient to be deployed in high granularity and agility in this rapidly changing environment. So we find that because of the lack of suitable technology,
Zhenyun, please skip to the punch. No more talk. Just skip to the slides.
Yeah, so we figured out Zappster really has an opportunity to partner with insurance companies and system integrator to provide the best solution to construction companies. And with that, I would like to, maybe Matteo, you can go ahead.
Oh yeah, that's fine. I will just would like to conclude, acknowledge the funding sources and all the collaborators and the students.
So thank you again, everyone, for joining us on today's webinar, and thank you for sticking around. We do have an upcoming webinar on September 2nd, led by Jimmy Oxley of University of Rhode Island and Miriam Fico of Smiths Detection. Thank you again, and enjoy the rest of your day.
Thank you very much, everyone.